Yeah, this is Tinkercad, very useful um, application, tinkercad.com. Here's the basic circuit down to its essential breadboard essentials. Yeah, so we have a yellow LED here and a NPN transistor, emitter, base, collector, and here's our tube here. Here's the red LED, and here's a battery, but it's actually a 3.3 volt signal from the Raspberry Pico. And that signal is a positive signal. So it's a positive 3.3 volts, which is energizing this bus here, and the ground is connected to the negative side of the battery. The LED turns on, light travels through the tube, or through air in this case, and here's the photoresistor. One side of the photoresistor is taps into the 3.3 volt bus, light turns on, and the current goes through the photoresistor, signals the base of the transistor, and when that happens, current flows through the emitter and then through the collector and then through this yellow LED, and which is the amplified signal here. And of course, current limited by a 220 ohm resistor. Both resistors, because they're tied to an LED, are 220 ohms. Now, we'll start the simulation, and that's pretty predictable. It's a very simple circuit. I mean, nothing new here. But notice this does something. I'm going to stop the simulation. So I'm going to effectively open this source circuit here. We stop it, and the LED on the secondary side of the amplifier turns off immediately. That doesn't happen for me. In fact, I have to tie it to a resistor here. We're going to place a resistor to ground, so we're going to effectively make a voltage divider here. Now we have a voltage divider. This photoresistor, one end is tied to the plus 3.3 volts. The other side is tied to oops. I think we better set the resistance on that, right? A 2.2 K ohm resistor right here. This is how I get this LED to turn off immediately when we lose the signal from this LED. So this is the tube here, that photo optical coupler. Whoops, what am I doing? Opto-Coupler here. And let's see what happens. Interestingly, the red LED, the signal LED, will always turn on. It's electrically isolated from this circuit here. So this circuit here is electrically isolated from this circuit. Light hits this photoresistor, not electricity, but light opens I should say closes, opens the door, but closes the circuit. And energizes the photoresistor. So in this circuit, we'll have to stop the simulation. In this circuit, this value needs to be, I'm guessing, really high. We'll make it high. 2.2 million. Now, what's going to happen is the resistance here is so high that it's going to be the bottleneck. So the current's going to take the path of least resistance, which is from plus 3.3 through the photoresistor and then to the base of the small signal transistor. We start the simulation and you can see the light turns on, the yellow LED off of the collector of the transistor turns on because the value of this component, this resistor, is so high. That works. Well, what happens when I do this is the higher this value, the longer it takes for this LED to turn off. And I have to wonder why. Okay, if I remove this altogether, this resistor, now we don't have a voltage divider here. We just have a straight resistor, photoresistor, going to the base. You start the simulation, the light turns on full blast, and we stop the simulation, not stipulation. But let's put a resistor there again and see what happens. I like to name everything. And resistance will be 2,000, 2.2 kiloohms, 2.2 kiloohms. The resistance here is, as far as this circuit is concerned, is low enough that the base current is too low to turn this transistor on in any meaningful way, because the current goes straight from through this resistor, through the photoresistor, and then to plus 3.3. That's because this path is the path of least resistance because of this low value resistor instead of the path through the base to the collector. Base to the emitter base. So the resistance of this emitter base junction right now is higher than the resistance through this resistor. But if we make this value much higher, let's call it 470K. Get some yellow in our life. Now what? We stop it and the LED is on. You can on enough that you can see it. We'll drop it down to 47. Look at that. You can actually see. I like this because you can change the values while the simulation is running. We'll drop it down to 4K. And now the light is almost off. 1K, of course, it's off. What does 0K do? It's off. A high value makes it go on a little better. None of this is what I wanted to show you. What I really want to show you is the primary problem. So I've solved the problem of the latency, the practical application of the latency. I can make that LED turn on or off quickly after the LED, the signal LED, turns on or off. I have solved that by putting a resistor here with the tied to one end of the photoresistor, so it goes to ground. And now we have a voltage divider to the base. Why is that? Why is it that this simulation doesn't show the actual reality of what's happening? So there's still a phenomenon, even though I figured out how to work around it. I'd actually like to know why it does it at all. I will start the simulation and the LED turns on. In the simulation, if I stop the simulation, the LED turns right off. But in the real world, remember I have these components, the LED and the photoresistor, enclosed in a pitch black tiny cylinder. No light can get in. This is not receiving any ambient light to keep it low resistance. So why is it when I turn the circuit off, when I end the signal here, stop the signal, the photoresistor is still in an on state, in the sense that it's low resistance, like a capacitor. It seems to like slowly discharge. That's what the behavior is like. And I don't know what the reason for that is. So I can get around it by putting a resistor here. And problem solved for me from the circuit point, from the practical point of view of a working circuit. So now this is an acceptable solution to me. In the previous video I said the behavior of this is unacceptable, that the LED takes a couple minutes to slowly discharge, whereas why is that? I don't know. So this is video 2, where I have solved one problem, but one other problem of physics remains unsolved. So we want a way to turn this LED off quickly after the signal has been removed from the photoresistor. We don't want this light taking a long time to turn off. And the solution to that problem is a small value resistor, 2.2K resistor here. And now you can see everything quickly. And I've tried this with, I did a pulse width modulation circuit here and different tests. And, there's always the photo coupling, even with a factory store-bought photo coupler, optical coupler. It's not as quick as a bipolar transistor with a base signal. Still quick enough for my purposes. Now, I still want to know, why does this photoresistor, if I remove this resistor that drains the current into ground, now all we have going to the base of this transistor is a signal, is a voltage, I should say current because it's a bipolar, is a current modified by this photoresistor. So I push the button, turns on great, but you can see it takes a long time to slowly dissipate. Why? What's here? There's not a capacitor. Is there some kind of, I want to know if there's anybody out there. So I'm asking because I don't really know. But I would like to understand